Hello everyone, the title of my thesis is Big Data Computing, Model and Algorithm Based on Spark Data Stream. The thesis mainly involves the following. Contents, Introduction Big Data Computing Model and Algorithm Based on Spark Data Stream Experimental Research on Big Data Computing Model and Algorithm Based on Spark Data Flow Experimental Analysis of Big Data Computing Models and Algorithms Based on Spark Data Flow Conclusions. Introduction in the race arc of BD computing models and algorithms based on Spark data flow. Many scholars have studied them and achieved good results. For example, King Chao has proposed to build an ensemble weighted classifier ensembles algorithm. The main idea is to divide the sliding window into multiple sub-windows, and build a decision tree on each sub-window, and use a certain method to select the decision tree with the best classification effect, according to the classification accuracy of each decision tree as its classification. The classifier, or assign different weights according to the classification accuracy of each decision tree, constitute an integrated weighted classifier. Pasternak proposed an incremental stream data classification (SPAC) model based on sample uncertainty selection strategy in order to solve the problem of concept drift. The model selects samples according to the uncertainty of the samples, forms a new sample set, and uses the sample set realizes the update of the original classifier and forms a new classifier using iterative classification technology. This article introduces the data storage system, resource scheduler, and Spark distributed operating platform, and successfully runs the improved algorithm in parallel on the Spark platform and obtains good experimental results. This paper uses the idea of density peak and maximum minimization criteria to improve, and proposes an improved canopy commence algorithm based on density peak. Finally, the improved algorithm is realized using the Spark framework, our big data computing model and algorithm, based on Spark data stream research and improvement of canopy commence parallel algorithm based on Spark improved canopy commence algorithm, based on density peak. This paper uses the idea of density peaks to calculate the relatively high density point in the data set as the initial clustering center point of the canopy algorithm, which solves the problem of the canopy algorithm, randomly selecting the initial value, and at the same time eliminates the noise points in the low-density area from the data set. Then, using the combination of the maximum and minimum criteria and the depth value, the selection process of the center point is optimized, which not only makes the algorithm not easy to fall into the local optimum, but also solves the problem that the algorithm needs to set the distance threshold manually. The idea of local density peak is based on the concept of local density. By presetting a distance radius, a circle is drawn with a point as the center, and as the radius, and the number of points falling in the circle is this the local density of the point. The point with the highest local density is the peak density point, and the local density is defined as, suppose the data set to be clustered. The corresponding index set are the data points, and when the data points are discrete values, the local density is formula E where j and I are not equal and both belong to the function g. X is formula 2. Among them represents the cutoff distance which is the preset distance radius, which is the distance value of the 2 to 5% position after the distance between all data objects is arranged in ascending order, usually 2%, and the value of is to Euclidean distance between points, the maximum and minimum criteria, and depth value the essence of the maximum. Minimum criterion is to ensure that the initial point is selected as far as possible. The main idea is, first, randomly select a point in the set as the initial seed point, and mark it as point A. Then calculate the distance between all remaining points in the set and point A, and choose the farthest point B as the second seed point. Calculate the distance between all remaining points in the set and point A and B. Find the two closest points of the distance, A and B, and choose the largest of these 2 points as the third point C, using the above method to calculate until the conditions cannot be met. All seed points can be selected, which can be expressed as follows. 3点 In some cases, it is necessary to add a threshold to the minimum distance. If the distance between points A and B, then, and the value of is usually 0.5. The unparalleled design of improved algorithm. The main idea of algorithm parallelization design is to distribute the algorithm that was originally running on a single machine to multiple nodes in the cluster to run simultaneously. Generally speaking, the parts of the algorithm that are not strongly dependent on intermediate results are placed on each node for parallel calculation. This saves the time and resources that nodes spend communicating with each other. The general process is to divide the data storage to be processed into multiple copies, and place them on each node, perform local calculations on the nodes, and finally summarize the calculation results, and update them to the global for the next step. The parallel design of the improved canopy commons algorithm based on density peaks in this paper is mainly in 2 aspects. One is to calculate the local density of objects in the dataset at each node, generate local seed points, and the other is to perform k-means on each node, optimization of clustering algorithms. The k-means algorithm and the BERT clustering algorithm have their advantages and disadvantages, especially the BERT algorithm is sensitive to the scan order of the dataset, so it is necessary to adjust the order of the dataset. Data aggregation pre-processing faced with the compression processing of a large amount of data. This article proposes to focus a certain piece of the dimensional data to a certain point of the data, which can simplify the large amount of data, and even reduce the data to 1/5, 1/10 or more. How much the clustering data can be reduced and fine-tuned the parameter values in the experiment according to the quantity and quality of the data, given a parameter point. For a d-dimensional data point, gather it to a specific data point is as follows. Formulas for each d-dimensional data object in the dataset. The parameters of each data can be the same or different. Under the same measurement of d-dimensional data, the parameters must be the same, otherwise serious clustering deviations may occur. In order to make the parameter have a unified measurement standard, we add another parameter to adjust the measurement size flexibly. The formula is as follows. Wood data sorting, processing, the research and analysis of the BERT algorithm. In this article, have learned that this algorithm is more sensitive to the scanning order of the data. Different insertion orders may allocate the data to different clusters. It is likely that the clusters are still quite different. The data that should be divided into the same cluster is divided into different clusters because of the different order. For the data problem of the dataset, we adopt a mathematical method called full permutation. The definition of full permutation is to select m that is greater than or equal to m numbers from n numbers and arrange them in a certain order, which is called take a permutation of m elements from n elements. When m 等于 n, all permutations are called full permutations of n elements. The number of permutations is the factorial of n, denoted as n. For the processing of full permutation, this article adopts a recursive method. For clustering 1, clustering 2, and clustering 3, first keep clustering 1, perform full permutation on clustering 2. Cluster 3, recursively use the full permutation algorithm, and then keep clustering 2 unchanged. For clustering 3 full permutation, cluster 3 there is only one permutation, and then perform the above operations with clustering 2 and clustering 3 in the first position to get all permutations. 3 experimental research on big data computing, model and algorithm based on Spark data. Flow performance analysis of algorithm parallelizations. Performance analysis of the algorithm is a standard embodiment to test the quality of the algorithm. The performance comparison between the algorithms must be compared with a large amount of experimental data. The experimental data must be converted into the performance comparison data according to the performance evaluation formula. Let everyone clearly and accurately see the performance pros and cons of line graph and histogram state, acceleration ratio, speed. For the execution time of the algorithm, suppose that Ts represents the time consumed by running a task serially in the case of a single processor, and Tp represents the time consumed by executing a task in parallel on multiple processors. Then the definition of speedup is the ratio of the time consumed in serial to the time consumed in parallel. The formula is as FOLLWSRO. The speedup formula. It is obvious that the speedup ratio of parallelization describes the degree of acceleration of the overall execution efficiency by the way of parallel execution of task. The greater the value of speed, the greater the ratio of Ts to Tp. When Ts remains the same, then Tp will be smaller, so the execution of the parallel algorithm can be derived the higher the efficiency. Therefore, the numerical value of speed is a direct manifestation of the running efficiency of the parallelized algorithm and the efficiency of parallelization algorithm, EP, assuming that P is the memory resource occupied by running a task. The efficiency EP of the parallelized algorithm can be defined in this way. EP is the ratio of the speedup speed to the running memory resource P. The specific formula is as follows: for a task that runs in parallel, it is likely that the speedup of its algorithm execution is larger, but it may not be so high in terms of resource utilization. Therefore, the acceleration ratio is not convincing in terms of resource utilization, so the efficiency of the algorithm can be reflected by the ratio of the acceleration ratio on the running memory resource and performance comparison of parallel algorithms. At the performance comparison of the algorithm, this article will compare the running time and the parallel computing speed-up ratio. It mainly focuses on the comparison of the parallelization experiment of k-means on the basis of the BERT algorithm, combined with k-means. To improve the BERT algorithm, the improved algorithm obtains two sets of experimental data according to whether or not to use full permutation in data pre-processing stage. One does not use the full permutation operation, and the result is obtained by directly running the data on the distributed platform through the improved algorithm. The other is to use the full permutation operation. The data is arranged for operation, and the aggregation and simplification of the data is for the full arrangement of the clusters of the initial k-means rough clustering. When the number of regions are, each region must be calculated in parallel with the improved BERT algorithm, and compare the results of each permutation cluster for weight comparison. 4. Experimental analysis of big data computing models and algorithms based on Spark data. Flow comparative experimental analysis of algorithm running time. This paper conducts a comparative study on the running time of the three algorithms, and the experimental results are shown in Table E, as shown in Figure E. It can be seen that the running time of the fourth data point has jitter on each curve. According to the results of multiple experiments, it is found that it is the result of the quality problem of the initial dataset. For different datasets, the running time of the algorithm may be slightly different, and the k-means algorithm is used in experimental algorithm, so similar running time jitter will occur. For the same data, experimental analysis of speedup of algorithm running data table R is above the speedup ratio of the improved algorithm without full permutation, and the improved algorithm with full permutation as shown in Figure R. The overall acceleration ratio will have up and down jitter, indicating that the early operation of the improved algorithm is not stable. Due to the small amount of early data, it will cause certain fluctuations in the algorithm during the execution of multiple sources when the data is running. But regarding the gradual increase in the amount of data, the speedup ratio gradually stabilized. From the experimental data, the speedup ratio has a slight upward trend. It can be seen from this that as the amount of data increases, the stability of the algorithm has reached more than 98%. The effect is better. So this algorithm is a parallel algorithm that is more suitable for massive data processing in the Spark cluster. Conclusions. This article focuses on the comparison of experimental data between the original algorithm and the improved algorithm. After many experiments on the Spark platform, the experimental data was analyzed and compared. The display of the data table and the line graph proves that the improved algorithm has better performance than the original. For the analysis of cluster datasets, this paper pre-processes the datasets according to the given formula and gathers some datasets to several points, so as to simplify the number of data. The specific processing logic can be implemented in parallel using the Spark distributed computing platform. Thank you.